Hello, so welcome to another edition of Science of the Times. Nice to see you, Tim.
Lovely to see you too. How are you doing?
I'm doing fine, yeah, all good. But you're doing really well. You're off to exotic parts, right?
I've got a quick trip. I fly out tomorrow morning to Hong Kong. I give a talk in Hong Kong, and then I go to Singapore where I do the same, and then back. So it's tomorrow, whenever this comes out, but when we're recording it, tomorrow is Saturday, and I come back on Thursday.
Gosh.
So I'm traveling quite a long way around the world, and actually. This week's podcast is about how the Earth came to be and why it's like it is.
Yeah, absolutely. And our guest is Jamie Woodward, and he's written a book all about the history of the planet.
Yeah, The Little History of Earth by Yale. I've not met him before. I read his book. Actually, I was asked whether I'd like to read it and provide an endorsement, which I did, and I really enjoyed it actually because it's interesting. Sometimes you get asked to provide an endorsement and you read the book and you think, I honestly can't think what I would say, but this one was easy. It was very easy to rave about. It's a great book, and I hope our listeners think about buying it.
Cool. So, should we get him on?
Let's get him on. Well, thank you very much for joining us, Jamie. I wonder if you'd like to introduce yourself and say a little bit about who you are.
Sure, great pleasure to be here. Well, I'm Jamie Woodward. I'm a professor of physical geography at the University of Manchester, where I do research and teach on landscape change and environmental change.
Fantastic, and congratulations on your new book, which is just out, A Little History of the Earth, and that's published by Yale University Press. A really good read, well worth it, and a fantastic stocking filler for any ages.
Thank you so much for saying that.
Before we dive into the book, do you want to say a little bit about a bit more about your research and what you sort of do in your day job? So I think you're kind of interested in quaternary environmental change and human activity in ice age environments, if I've understood it correctly.
Yeah, I'm interested in a range of things actually, but so the Quaternary is the most recent geological period, covers the last 2.5 million years. So that's where most of my research sits. So I work over sort of quaternary timescales, but I also work over sort of modern and historical timescales. I'm interested in contemporary processes as well. So much of my focus is actually on rivers. So I'm interested in how rivers behave in the present day and how humans interact with them. And I'm interested in how rivers behave in the past, right back to the Ice Age and beyond.
And quite a lot of your field work is in the Mediterranean area, if my digging around on the internet is correct.
Indeed, I did my PhD in Greece actually, working with archaeologists actually, looking at some Ice Age rivers and Paleolithic settlements. So there's a thread that runs through my research that goes right through to the sort of microplastic stuff I've done recently. Is basically how humans interact with rivers.
No, fantastic stuff. But your book is much deeper time than that.
Indeed, yeah. So this is probably my most ambitious writing project to date. So I sit very much in the Quaternary period, but I'm also interested in earlier geological periods, and I actually teach a first year course, a large course of physical geography, where we focus on the last 66 million years and the sort of the major climate changes for when the Earth was very hot into the present sort of cooler period. So I do delve into the deep past, but yes, it was a big challenge for me to take on the whole span of Earth history.
So, what inspired you to write that and tackle such a big topic?
Good question. And I asked myself that question lots of times when I started doing it, because there's lots of. I like the format of Little Histories. Maybe I'll come at it that way, because the format of Little Histories is that they're 40 chapters, approximately 2,000 words per chapter. So there's sort of set of essays, really. And a good friend of mine, Nigel Warburton, wrote a Little History of Philosophy, which was very successful. And so he tackled the whole of Western philosophy in sort of 40 bite-sized chapters. So I thought it would be a challenge to take on the history of the Earth in that format. And the original Little History book was written by a man called Ernst Gombrich, who wrote a Little History of the World, a history of people, a political history. Right. He wrote his book in 6 weeks.
Wow.
So there were a whole set of challenges associated with this, but I liked the format, and I wanted to see if that would work to take on the whole history of the planet.
And how many did it take you? A bit more than 6 weeks, or?
Yeah.
No.
Much longer. Yes.
Yeah. No, well, congratulations. It's a really good read and it is really accessible.
Thank you.
And I actually agree with you. I like that format because 2,000 words you can dip in and you can read a chapter, even if you've only got sort of 15 minutes or so, spare time. So no, it works really well. So I guess the Earth formed what, about 4.5 billion years ago? That's when the solar system formed. Is that right?
Yes.
And how did it come about? How did it all start?
Well, you've written about this, Tim. You know all about this. So, and I had to sort of really delve into a lot of stuff that I knew about, but I hadn't taught and I hadn't researched and written about. So I started reading about accretion and the formation of the solar system. So about 4.5 billion years ago, we had the formation of the sun and the solar nebula, this huge disk of dust and rocky material. And then gravitational processes took over and we started getting the formation of small planetesimals, and this accretion process is where these particles are attracted together, sort of billions of particles attracting one another and gradually forming into larger bodies, planetesimals, and eventually planets, which produce the rocky planets and then the ice planets and the gas planets in the solar system. So we still don't fully understand all of those processes, of course, but in broad terms, that's kind of broadly what happened.
And so I think, just sort of going really back to basics, a theme is this concept of deep time. Just for our listeners and viewers, can you tell us what you mean by deep time?
Yeah, well, deep time in terms, millions and billions of years, right, to sort of the early history of the planet. But the idea of deep time was kind of formulated by James Hutton, one of my heroes, who was a sort of Scottish geologist, natural philosopher, who worked and wrote mainly the second half of the 18th century. And he was the first person really to write about, the Earth having a very, very deep, long history. Now, of course, you couldn't put a number on that. They didn't have any scientific dating. But he put forward the ideas that the geological record could only really be explained by having lots and lots of time to explain the rocks and the erosion features in the geological record.
And I mean, it's really hard, isn't it, I think, for people to get their head around quite how long even 1 million years is, let alone 4.5 billion years. I mean, that was kind of one of the things that I find people really struggling with. I mean, have you got any sort of tricks, to try and illustrate quite how vast amount of time the Earth has been around?
Well, one of the favourite ones, and it was one of the favourite ones of Stephen Jay Gould as well, is the outstretched arm.
Yeah,
in my arm here. So the origin of the solar system, the origin of planet Earth, is on your shoulder here, and then moving this way down to your elbow, down about. So this is about 4.5 billion years ago, down to your elbow. The sort of lot of Precambrian time, about 2.5 billion years ago, you started to get the first life in the oceans, and then keep going down. Of course, the dinosaurs in the palm of your hand, and then eventually humanity right at the sort of tip of the fingernail on the middle finger. So that's a nice analogy to illustrate deep time. But it's hard to think about those vast numbers because we live very much in the present. And one of the challenges for the book was, how do I allocate all that time into 40 chapters, and how much time do I allocate to the Precambrian, or the last 4 billion years, which is 88% of Earth history. So that was a challenge as well about how to compartmentalize those stories into the book.
Sure. And so, Jamie, there's it's, as Tim said, it's very difficult for us to sort of get our heads around this idea of time and deep time and just the scale of it all, temporally, but also in terms of processes, sort of earth-shaping processes. Do you feel that there's some that are vastly misunderstood by the public?
Well, you mean like plate tectonics?
Climate shift, this sort of thing. Just these big, sort of macroscopic processes that have shaped the planet.
Yeah, so sort of planetary scale processes, and what's interesting when you sort of read about Earth history and read about the processes is very often, if you do geography A level, for example, or Earth science, it very much focuses often on the surface of the Earth, and plate tectonics is very much framed in terms of hazards of where the earthquakes are, where the volcanoes are, where the tectonic plates meet, and often much less on the actual processes that are driving plate tectonics, and that's fascinating. And also, a big question: when did plate tectonics begin? Because Earth is the only planet in our solar system that has fully active planetary scale plate tectonics. It's one of the things that makes the Earth system unique. And then, of course, plate tectonics over much longer timescales influences the climate, the composition of the atmosphere, and life itself. So plate tectonics is a critical feature of the Earth's system, and maybe that's not quite so widely appreciated as it could be.
And they got going quite a long time ago, as far as we can tell. I mean, I've seen those. And you talk about this in the book, obviously, but I've seen those videos online where you sort of see the continents, the ancient continents coming together and going apart, Pangaea, and as I like to jokingly call it, began to trouble British Gondwana land, and them floating around everywhere. When did they really get? What's the best guess? Can you remember? I mean,
I think there are. There's the sort of early plate tectonics that there's signs in the rocks, or some of the ancient rocks, that there's sort of there's sort of pillar lavas, there may be subduction zones, right back sort of 4 billion years ago. So some early plate tectonics, and it's interesting that how did plate tectonics begin? Did it begin on a local scale? Was it a stop-start process? It may have started and then stalled. But certainly by about 3.5 billion years ago, plate tectonic processes was a planetary scale processes was well developed. And you mentioned Pangaea there. What's also interesting about Earth history is that that's probably the supercontinent people are most familiar with, the one that was defined by Wegener. But Earth has gone through several sort of supercontinent cycles of the formation and the breakup of supercontinents, and that's another interesting feature of Earth history that isn't widely appreciated.
Because the continents are spread out quite a lot at the moment, aren't they, compared to certainly sometimes in the Earth's history?
Indeed.
The ones we've got, yeah.
So there are during Pangaea, for example, say during the Triassic and the Jurassic, when the dinosaurs were around, and many of those dinosaurs were striding around on a supercontinent. So you could walk across most of the existing continents because they were joined together, and it's predicted in 250 million years in the future the continents may well be joined together again. So that cycle will continue.
And so, Jamie, in doing all of the research for your book, were there some ideas that maybe you had, and sort of any recent developments or recent research that has sort of thrown those into question, or has there been anything like that at all? Has changed the way you've thought about things?
What changed my way of thinking about things? I hadn't thought about this actually.
Sorry, I always ask the question that.
Sorry, I'm just trying to think of something that really did make me stop and think and make me change the way I thought about something. But one of the ideas that I do talk about in the book is that about how mountain building can change the climate.
Yeah,
and this is an idea I teach at first year. Actually, a lot of students find quite challenging, and also it's related obviously to plate tectonics changing the climate. It's called the uplift weathering hypothesis. It was put forward by Maureen Ramo, an earth scientist who's based at Columbia in New York. The idea that the formation of the Himalayas, for example, was largely responsible for the global climate cooling we see over the last 50 million years or so. And Maureen Ramo is one of the sort of great women in earth sciences, and a great sort of hero actually and I use her as an example in my first year classes, because she got a lot of stick when she put forward that model with Bill Rudiman in the 1980s, and it is broadly accepted now that so when mountains go up, you get a lot more weathering, you get a lot more erosion, and those minerals and those weathering processes involve interactions with carbon dioxide. So carbon dioxide is basically slowly taken out of the atmosphere, it combines with new minerals, and they get washed down to the ocean, and then fossils, not fossils, sort of forams, little tiny shells and corals, etc., use that carbon to make their shells, and then they get buried on the ocean floor. So when that process happens, is accelerated because of the formation of big mountain belts. Carbon dioxide is progressively sucked out of the atmosphere, so the climate will cool because the greenhouse effect is weakened. So that's a really big idea, actually. That's a relatively recent idea in the earth sciences, but it's also been really valuable because it's helped to explain climate cooling in the past as well, in deeper time.
So one of the most remarkable things that happened in Earth's history is obviously the emergence of life and how life got started, and that's a a very complicated process. So we don't know a lot about it. How did you go about addressing that in the book? Because that's something that I really struggled with when I was kind of thinking, how on earth do you deal with something like that?
Well, this is your expertise, Tim, and I mean, you struggle with this. It's interesting. When I wrote the book, I thought, well, the first half of the book, writing about sort of the deep time, would be really hard, and then when I get to the second half of the book and the more recent geological periods, I kind of that will be much faster. Then I'll be able to get on with it. And then I found that I knew too much then, so that it got even slower. So what do I leave out? So I couldn't win. But in terms of the evolution of life, we still don't understand those big questions and some of the processes. And I talk about the sort of the two main environments, and correct me if I'm wrong here. The idea that some of the processes happen on spreading ridges where you've got lots of sort of minerals and fluids coming out of the mantle into the oceans. That sort of mix of chemistry and energy could have driven the early forms of life. Alternatively, they could have been on sort of salty lagoons in the bright tropical sunshine. That might have been the cradle of life. We still don't fully understand that, but they're two of the candidates that I write about, and I kind of leave it as an open question, I think.
Yes. I think I did pretty much the same.
That's a relief. Yeah.
Sorry, Syma, you're going to say something.
No, sorry, no. It was just, but I was just wondering, sort of, given that you do now have this kind of broad picture that you paint so nicely in your book, if you could choose a period to go back to and witness, what do you think, witness events unfolding ahead of you? What do you think you would choose and why? Wow,
what a question. I mean, I think they'd probably give you a very long list of things I'd like to go back and see. But the Cryogenian, for example, snowball Earth is a fascinating period, because one of the things that's, I think, become apparent in the Earth science is maybe this is an answer to the question you asked me earlier, Syma, about. Is that, the Precambrian, the first 4 billion years of Earth history, were often seen as a sort of geological dead end. There weren't any fossils, there wasn't, just a few blobs and evidence of primitive life, and it was a kind of not worth studying. And all the excitement was in the Jurassic and the Cretaceous and the Cambrian, where we had complex life. But the Cryogenian is a really interesting one. This is the period where we think there were snowball Earth events, where the planet was frozen. And there are big debates to the extent to which the Earth looked like a snowball and the extent to which those, but we certainly had big ice sheets in the tropics, large glaciers in the tropics, so very different from the scenarios that we have today. But also shortly after this was the time when complex life evolved. So there must have been life surviving beneath these ice sheets and beneath this sea ice. And then towards the end of the Cryogenian, we get very rapid global warming, driven by volcanic activity. And so we have these glacial deposits that are overlain by tropical limestones. So the climate flipped profoundly from a sort of deep Arctic conditions to tropical conditions. So that was a really interesting period where, the habitability of the planet was under threat. And yet it flipped from super cold to super warm. And the irony there is that in the following period, the Ediacaran, we get complex life forms. And it may well be that the glaciation was putting lots of erosion and lots of nutrients into the oceans, and that might have, turbocharged evolution at that time. It's a really interesting period.
And then just, so as you say, complex life really took off, and the Ediacaran, we start to see the first animal communities coming together. And then the Cambrian is the really exciting bit as well, isn't it? So that's when then you see this explosion in the Cambrian explosion in all sorts of new forms and what have you. Any kind of particular animals or innovations, evolutionary innovations from that period that really caught your attention?
Well, the Cambrian explosion is fascinated, geologists, paleontologists, evolutionary scientists for 150 years and longer. So just all those life forms suddenly appeared, and there's just new ways of moving around, whether you were burrowing and scurrying across the floor, the early swimmers, etc. And the Cambrian is fascinating because I also write about, the idea of it being Darwin's dilemma.
Yeah.
It's suddenly, for a long time, people thought, Precambrian, just a few simple cells and life forms, simple life forms. There's suddenly this Cambrian explosion, but Darwin's, it didn't allow enough time there for evolution to happen. And Darwin was kind of seriously worried about this, that it might be hijacked by creationists, for example. But we now know from the study of the previous geological period, the Ediacaran, is that complex life forms evolved and occurred much, much earlier. So yeah, the Cambrian is still a remarkable period of evolutionary diversity, where you get all these weird and wonderful life forms, particularly from the Burgess Shales in North America. And so some spectacular life forms and weird and wonderful creatures like shrimps with 5 eyes, for example. It's a remarkably interesting period. But also we now know, because of dating, that actually the explosion took place over tens of millions of years. It didn't happen overnight. So there was enough time for evolution to take place. So it kind of does fit within Darwin's model. It makes sense. But it's an interesting kind of, the ideas around that are really interesting, about how people struggle with the explanations for that reality of the fossil record.
Sure. I mean, just as a sort of a scientist at the more molecular scale of things, I guess, a lot of those sort of extremophiles that you talk about that existed in these extreme sort of frozen environments and stuff, if we could bring them back, there's probably a hell of a lot we could learn from surviving in these extreme weather conditions. It might even be useful now, right?
Yeah, indeed. And actually, thinking about snowball Earth events and what's going to survive between the ice sheets. I mean, some of the recent work in Antarctica, looking at the life forms on the bed of the Southern Ocean and on the seas around Antarctica beneath the ice shelves, showed incredible diversity of life forms at the present day. So it's not unusual, therefore, to expect maybe similar diversity in earlier geological periods under those harsh environments. So another answer to, maybe this isn't the answer to your question, Sam, but I'm thinking, you said, do you want to go back to another geological period? One of the things in the book is I write about a lot of the characters and the scientists and the people who kind of made a lot of the key advances. I would like to have a stroll along the beach with Mary Anning. That would have been fun. Back to the 1820s to maybe after a big storm in Dorset, and see some of the fossils emerging out of the Jurassic cliffs there. That would have been an interesting insight.
So, I mean, one of the themes that kind of runs through your book is as we talked about snowball or Earth, but the fact that the climate has swung backwards and forwards, sometimes, as you say, reasonably quickly. And what do you think the sort of deep time climate variability teaches us about life's resilience, but also, I guess, its fragility, on Earth, and any lessons for us going forward?
Absolutely. I mean, key lesson, carbon dioxide, we know greenhouse gases have been a key driver of climate change over millions and billions of years. And so that, very often when the climate has been warm in the past, it's because carbon dioxide has been high. We've had super greenhouse conditions, and the various processes have weakened the greenhouse effect, and the climate has become cooler. So and most recently in the ice core records, say, in the Pleistocene, the Quaternary period of the last 2 million years, we show that carbon dioxide and global temperature are in lockstep. So the lessons for now is that we understand what drives the climate system, and the warming of the planet over the coming decades will be determined by how much carbon dioxide we continue to put into the atmosphere. So the lessons from the geological record in that respect are very, very clear indeed. What's also clear is that in the past, the natural processes driving those have happened rather slowly. And we're not going to be saved by those natural processes. It's up to us to try to reduce carbon dioxide concentration in the atmosphere, or certainly to limit their increase.
And are you an optimist?
I am. I'm always an optimist. I think one of the themes in the book is that I talk a lot about the habitability of the planet and the unique set of ingredients that make Earth habitable. And then but that habitability isn't guaranteed. It isn't something we should take for granted. I mean, look at Venus and look at Mars. They're in the habitable zone of our solar system, but things went badly wrong there in the past under natural processes, and we're currently driving the Earth to strong greenhouse warming more rapidly than we've seen in the recent geological past. So I am optimistic. I mean, I do a lot of work on water pollution and microplastics in the last few years. And I've seen real change and investment where activists and campaigners are making the most noise. So if you're concerned about the environment, get involved, ask questions, be active, and that can be a seed for change. So I am an optimist.
And so, yeah, just on that note, I mean, would you care to speculate, given sort of, current trajectories and things sort of geopolitically, what the next chapter might be for planet Earth?
Well, it's very easy to get depressed with the current political situation. I mean, look at the recent COP conference down in Brazil, and I think the number of delegates there were almost outnumbered by the number of lobbyists for fossil fuel firms. So the politics is going to get nastier before it gets better, I think. But we understand the fundamental processes. And actually, interesting, I think maybe it's insurance firms and investment in green infrastructure and in more sustainable ways of developing a sustainable production of energy, green energy. That is the way forward. And even if some of the politicians at the time are arguing against that, I think the insurance companies and investment is still happening. And look at China's producing more solar panels and more wind farms than anybody else. So I think those changes will happen. Whether they'll happen quickly enough is a moot point. It's hard for anybody to say. But I'm optimistic that things will get better.
Good. So one of the themes that runs through your book, and something that I think is fascinating as well, is the sort of the way that the way that Earth has shaped life, but also the other way around, the way that life has kind of shaped Earth in terms of whether it's the cyanobacteria helping oxygenate the atmosphere or what have you. And how do you kind of go about dealing with that interplay in the book? What's the sort of the sort of key feedbacks that really impressed you?
Yeah, well, I talk very early on in the first chapter about sort of we were thinking very much on this journey of the Earth, is thinking about the Earth as a system, and thinking about this, the great spheres of the Earth, and one of those, of course, is the biosphere, which starts to kick in, in terms of, you mentioned there about the production of the production of oxygen and increasing the oxygen content of the atmosphere. So that was a critical milestone, what's known as the Great Oxygenation Event, with when the oxygen concentration of the atmosphere increased, and which then eventually allowed complex life forms to develop. So that feedback is really very, very important. And then more recently, right back to into the ice ages, for example, the swings between carbon dioxide production and global warming, global cooling. And one of the things that even very, very recently, it was Keeling, who produced the Keeling curve, for example, was the first person to recognize that carbon dioxide increased, and decreased on a seasonal basis in relation to biomass production in the northern hemisphere, in terms of the production of leaves and life forms and plants in the springtime, and then of course in the fall when those leaves die and they degrade, and the seasonal cycling of carbon dioxide and the seasonal cycling of warming over that period is a really interesting feedback, actually.
So I think we're kind of running out of time because we're unfortunately it's gone incredibly quickly. But really enjoyed chatting to you, and congratulations again on a fantastic book, A Little History of Earth, published by Yale. Do you have a final question, Syma, you want to ask?
Not really. I just want to encourage people to have a look at Jamie's book and buy it for Christmas, because it's great.
Thank you very much, Jamie. It's been a pleasure talking to you. Thanks for taking the time.
Thank you so much for inviting me. I've thoroughly enjoyed it. Thank you.
Yeah. What do you make of that then, Syma? The history, 4.5 billion years in half an hour.
Oh, it was excellent. I thought it was really interesting and really well contextualized.
I know. When we moan about the weather now, when you hear about ice house Earth, ice ball Earth, whatever it is, snowball Earth. You hear about snowball Earth, you realise that a little bit of rain isn't quite that bad.
Yeah, and especially if to survive, I have to have 5 eyes or whatever it was he said.
Oh, in the Cambrian explosion.
Right.
Yeah, some of those organisms are really difficult to interpret. The fossils and yeah, we don't. I mean, we don't know a huge amount about a lot of them, but it was clearly an era when life really took off. It's when sense organs and organs came to the fore. It's when brains came to the fore, and it's when predation got going. It's when things learned to eat one another. So, which is quite cool.
And I mean, even though, I've sort of been in and around biology, around biologists now for a long time as a trained chemist, it's still hard for me to get my head around some of these concepts, and especially so many species that are now extinct, right? Yeah. And the diversity of life that changes, although it's not fast in the grand scheme of things, on our level, it is fast. And it is, I think he explained it all really well.
No, he did. He did. I mean, the scale, as you say, the timescales that you're working at when individual reactions are going, which is in microsecond, mini microseconds, or whatever
Yeah.
they're called, versus billions of years, and then going from from individual atoms and electrons interacting with one another, well, interacting right the way through to the planet and the solar system. I mean, it's just astonishing how much science has kind of learned and uncovered, I think.
It is, yeah. I think we could give ourselves a pat on the back as generally as a species. I mean, we've unearthed quite a lot, right?
We have, but we've also, we're changing the planet, and not necessarily a good way for us. Life will survive, but if we do decide we want to kind of try and clean up the planet, we will do it because we realise that we're hurting ourselves rather than hurting anything else.
Yes, that's right. It'll be a dire need to get on with it and hurry up and do it, right?
Yeah. Well, I think that next time, and probably the last one before Christmas, we're going to do a science for Christmas, just you and me, right?
Yep, let's do that. Okay.
So you're going to ask me about Christmas animals, and I might ask you about the biochemical reactions that go on after a huge Christmas lunch with a little bit too much port.
Yeah, absolutely. I think that'll be fun. Let's see how we go.
Let's do that. Great. Well, great to see you, Syma, and talk to you soon.
Yeah, safe travels, Tim.